Okay, thank you very much. So I'm going to update you on what has happened in the past couple of years in the AGORA project, AGORA High Resolution Galaxy Simulations Comparison Project, and it'll be a nice lead-in to the continuing weekend sessions. So it's the kind of talk that I have to give, like I'm obligated to give as a project coordinator, not the exciting science that I do. It's probably less sciencey. It would be a meta-science talk, but that's not to say that this is not important. It's probably important, and at the end of this talk, I'll convince you that this is something that you have to always pay attention to, the reproducibility of the numerical galaxy formation simulations. So we're scientists, so we always strive to make sure that every single experiment that we do is reproducible before it gets established as a solid scientific knowledge. That's the fundamental principle of scientific method. We strive to do that. We sometimes risk our lives to guarantee the reproducibility. But how are we actually doing it? So last year, there was an article in the Nature magazine. There was a survey of more than 1,500 researchers, and they asked this question across multiple different disciplines. They asked the following questions. What fraction of the studies, published studies, that you see in a respected journal of your field, do you think is reproducible? Of course, it varies between different fields by fields. In medicine, it's like 50%. In physics and engineering, probably astronomy belongs there, 80%. So we're doing better than the other guys, biology or medicine, but something to think about. So that's what the Nature magazine put it as a reproducibility crisis. So there are lots of reasons that they speculate why, but I think it's the perception issue, like how much do you trust your peers? And that goes to how much the public can trust you. And the article goes on to say it's related to the public funding if you're heavily relying on the public funding, just like ourselves. So it's something that you have to, just cannot ignore. So in the other fields, they're trying to cope with this. For example, in psychology or cancer biology that heavily relies on public funding, they have this reproducibility project. This is their webpage, launched in 2011. For example, in psychology, they have done this massive project trying to replicate exactly 100 published studies, well-known studies in their field over like many years. And the finding published in 2015 was really interesting. So here, this is a psychology. It's notorious to in reproducing the published results. So in the x-axis is the original effect size, whatever they saw in the original study. Y-axis is the replicated study. Ideally, you may want to see the data points lying on this y equals x line, but obviously that's not happening. And what's alarming is that it's not the normal distribution around that y equals x line. It's more towards here, meaning if you think about it a little bit, the original study was pushing for some, sensational results, right? And what's more alarming is the data points here. What that says is not only the original study was not reproduced, but actually the opposite was found. So it's something to think about. And then this study, this particular study, there was a question raised whether this study is reproducible or not. So, right, so that's the other field. Obviously, the other fields are paying attention to this issue. So how about us? How about galactic astronomy? How about the numerical galaxy formation community? Obviously, we're doing okay, right? Right? So the success of the galaxy formation theory, I think, relies heavily on the robust and reproducible numerical experiment, because that's the only tool that we can really use to study the galaxy formation. So, but there hasn't been a lot of effort towards this goal of guaranteeing the reproducibility until we launched this AGORA project. That was to compare different simulations with a constrained common physics and common inertial conditions and common analysis tools to make sure that the simulations are reproducible across the field, across the codes, and to collectively raise the predictive power of the numerical experiment. That way, we can guarantee that the observers pay attention to us. Otherwise, we're going to lose our audience because we cannot trust ourselves. How can we say others to trust us? So that was the consensus that we had a few years ago. And this diagram is the AGORA infrastructures that we have built over the past few years. It was a wishful thinking just a few years ago, but it's now almost 99% complete with the common inertial conditions, common astrophysics modules such as Graco, common ICs by Music and MakeDisk, and common analysis platform that is code independent. All 9 participating codes can be read in and analyzed by the common YT platform. So we worked with those independent Music, Graco, and YT collaborations to push them and test their tools in our setting. And I think I'm confident that this tool can be used by anybody at this point, and it's fully ready. And it's also public, so you can just visit the webpage. So we had 2 papers so far. First one was the dark matter only comparison. I have no intention to go into the details of this paper, dark matter only simulations. And last year there was a hydrodynamics, gravido-hydrodynamics comparison in an isolated disk setup. So as you can see, we had 9 codes, again, as in the dark matter only comparison. For this, we carefully constrained everything that goes into the simulation, such as the ICs and the physics package. I'm talking about star formation, UV background, pressure floor, everything that you might want to have in your modern day simulations. Of course, not the cutting edge, your favorite feedback, but at least the ones that we can all implement in 9 different codes. And we impose the high spatial and temporal resolution so that it matches the modern contemporary high resolution simulations that you see in the literature. Again, this second paper had 35 figures. I have no intention to go into every single details. You're welcome to take a look at it. But the one point that I want to make is that at the end, all 9 codes agreed very well in multiple dimensions. As I said, 35 figures, that's quite impressive. And sometimes the agreement was as good as less than 10% at every single radii in this cylindrical profile, for example. So at the end, we kind of agreed that probably the modern day high resolution simulations, when carefully designed, aligned with the guideline that we proposed in this simulation, in this paper, maybe the result of that modern day simulation could be robust and reproducible, although in this limited sense. So what we found is that any intrinsic code difference between, say, SPH and AMR was smaller compared to any physical variation, such as in like doubling the supernova feedback efficiency, something like that. So right. So that's that. That was what the paper said. And now I'm going to talk about what the paper didn't say, because I think that's much more interesting. So actually it said something, but in like 2 sentences. So this is the PDF, density temperature PDF that we put out, 9 panels again in the paper. That was October 2016, right before the paper gets submitted. Then how did it look like 1.5 years ago? This is how it looked. So if you look at this, of course, the orders of the code was scrambled to not embarrass anybody. But you can see that a lot of things might have happened between those two moments. Like, I can tell you that the snapshots that I happen to store in between those two, I have 55 snapshots, 55 frames in between those two, meaning at least 55 iterations have happened between that, two time frames. Even to reach that picture, you have to first figure out the common ICs, common physics package. So it took many, like 2 years to get there. But then you have to do the iterations to go from there to there. So what happened? What was happening in those time periods? So 3 different things. Of course, there were like rare occasions of code errors fixed, identified and fixed. So that's great that we can help some code to identify their own codes, identify the errors in their own codes. And of course, there were some human errors, like obvious human errors, not understanding the IC properly. But most of them was about understanding your own codes better and understanding the other codes better, like your peers' code, so that the runtime parameters and your setting of the simulations can properly match what others are doing. So that was the major thing that we had to do. And I think this was a good thing because we were able to initiate a conversation between and amongst the code groups. It was something that wasn't happening. And what the AGORA means is right, just like this. Like we have to have some kind of venue that we can talk to each other to help understand others better. So I think that was summarized in like 2 sentences in the discussion, but I think it was worth mentioning in this talk. So I want to show you this one thing quickly. So I said there were 55 frames. I always thought that that's a lot, so I might as well make a movie out of it. So it is not the kind of movie that you have ever seen, so I'll just let it play. So it's 6 frames per second. So even if you think nothing is happening at one given moment, something is happening. So I'll just let it play again. It's just so relieving for me to just watch this because like 1.5 years of effort, I'm not just me, but the effort by like 40-something co-authors are just encapsulated in here. Just one last time. I like this movie so much. Okay, so yes. I'm just going to talk about it. So how did we get there? So it was obviously enabled by lots of workshops. We had 6 annual workshops so far, close to 20 telecons, and we had the infrastructure, we had the web workspace. So all allowed ourselves to communicate with others. And I think it was a human experiment in some sense. At the end, we obviously didn't intend to make it this way, but at the end, it was a human experiment, I think. After all, we published 2 papers, like 40-something co-authors each, all of them theorists, like lots of egos colliding, lots of near-miss moment of implosions, but at the end we survived. Just yet, not yet imploded. So I think it was a really fruitful experience for us as a community. So we built up this community spirit that I think is really useful to continue look at some of the science-oriented issues. For example, during the workshop this week, we talked a lot about the CGM and clumps, whether the simulations that we see are really robust. That's the question that some of you may raise. So the simulators are preemptively trying to look at this, whether the results that we see in simulations are something that we can trust. And the observations are coming online, so it's probably the right timing. So we're going to continue this discussion to launch these 2 science-oriented papers over this weekend. So I'll just put up the summary slide. I'll just say that the AGORA collaboration is here to stay. I think it offers a very unique opportunity to allow us to tackle the long-standing challenges in galaxy formation.
You mentioned it was starting at 9:30 tomorrow.
Yes, 9:30, but 9 breakfast. Thank you very much.
Out of curiosity, among the full set of participants, what was the range in the computing power that each group had? Did you have like order of magnitude range, so some people had to wait a long time to get something out, or pretty much similar?
You mean like how much time each group take to produce like the same?
Computing resources, would they all be similar?
I think one of the consensus that we made earlier on in this collaboration is we do not discuss that because, again, that may embarrass some group. So we had that particular discussion at some point earlier. So we don't talk about like which code is the most efficient or not. So.
This is a really effective secret side.
I mean, there has to be some, I guess, some privacy, I guess. I mean, I showed this 9-panel plot, but that 55 frames, I didn't even talk about like the internal iterations that each code group might have gone through to submit their entry, and then they might have to rerun after checking with others. But some process where we didn't necessarily want to like dig into every secrecy. Yeah.
So first comments. I don't think the AGORA project would be possible without the leadership of the community. So I think really
Thank you. I mean, I also want to say Joel, who supported all the workshops and telecon so far, and all the others who, suffered from my nagging emails and all that. Yeah.
Also a question, how much of the time do you think was spent relative in the 2 papers that will come out, right, between science versus political stuff? Groups not wanting to look bad as the exception to the rule. Like, what's the relative amount of time spent and energy spent on that?
You mean my energy?
No, just your energy is entirely for the participants.
Well, I can, Joel, do you have anything to say? My energy.
Diplomacy energy on Ji-hoon's part was certainly a very large, played a very large role in making these papers successful.
Yes, we can talk in private.